So thanks to the organizers for giving me this great opportunity to speak and to talk about this work which I've been doing with Lucille and Leon about thermal conductivity again. So just as a reminder, when a material is placed between a hot source and a cold source, there is a gradient of temperature across the material, and there is an energy current flowing, and they are proportional to one another and related by Fourier's law. And the proportionality coefficient, kappa, is the thermal conductivity tensor. On the diagonal of this tensor, there is the usual longitudinal thermal conductivity. But in this talk, I will mostly focus on the thermal Hall conductivity, which is not only the off-diagonal, but the antisymmetric part of this kappa tensor. And because of that, and because of the Onsager's relations, the thermal Hall conductivity is odd under time reversal, which means that the energy carriers are chiral and break time reversal symmetry. And therefore, thermal Hall conductivity is especially interesting in insulators because there it's not obvious how this can happen. Now, on the experimental side, there are not so many, but still quite a few experiments measuring thermal Hall conductivity in insulators, especially in magnets. So here are a few instances. And although we know that the energy carriers must be neutral particles, it's not always clear whether, it's not often clear whether they are phonons or magnons or both or something else. Now this is one experiment among others, but one where the answer is quite clear, which is in the cuprates. So on the left, we have the thermal Hall conductivity as a function of temperature for 4 different values of the doping, so 4 different materials. And we can see that the thermal Hall conductivity in the pseudo-gap and the multi-insulator phase are almost the same. Okay, so we are looking for energy carriers that are present in both phases. So phonons are a good candidate, but one could think about other neutral energy carriers, so maybe magnetic excitations. But now if we look at the right panel, we have, they measured the thermal Hall conductivity not only in the XY plane, which is the plane of the copper atoms where the magnetic excitations propagate, but also in the ZY plane, so orthogonal to it. And we see that the Hall conductivities in both cases are basically exactly the same. So this means that the energy carriers are quite insensitive to whether they are propagating within the copper atom planes or perpendicular to them. So this is a good clue that in that case, phonons could be the energy carriers because they propagate in a roughly isotropic way. But that's quite specific, but let's ask more generally, which theoretical methods can we use to compute the thermal Hall conductivity of neutral bosons, phonons, magnons, or other bosons. So first one can use a linear response theory. So just like there is a Kubo's formula for the electrical transport by electrons, in the case of thermal transport, there is the Kubo-Luttinger formula. And as Leon has emphasized in his talk, there are some subtleties around this formula. So instead, we wanted to use a different route and use explicitly the fact that we have well-defined bosonic neutral quasiparticles that are moving in real space and that are carrying energy with them. So we wanted to use a kinetic theory for these bosonic quasiparticles, which can also allow us to access not only the global energy current, which is provided by a linear response, but also the local energy currents, which is especially useful in inhomogeneous systems. Okay, so the kinetic equation we want to look for our energy carriers has this form. So it's an equation about this n function, which is the particle density in band n at momentum k and position r. And the kinetic equation gives us the time evolution of this function as a function of the collision integral, which depends on which accounts for the effect of all the interactions and collisions of the energy carriers between themselves and with other degrees of freedom. So in this talk, I will present 2 results that we have obtained. So first, we focused on the right-hand side of the kinetic equation and the effect of the collisions. And we studied in particular the skew scattering, inelastic skew scattering of phonons by other collective excitations. And then in the second part, we wanted to understand better how a Hall effect can also arise from the left-hand side of the kinetic equation and the intrinsic dynamics of the energy carriers. And I want to emphasize at this stage that this would be only about collective phenomena, so the energy carriers are collective excitations, phonons or magnons, and they scatter with other collective excitations. Okay, so our starting point to study the thermal Hall conductivity of phonons, that's my first part, is to write down Boltzmann's equation for the phonon population, and here. And we want to focus on the right-hand side. So for the left-hand side, we take a very simple convective derivative where the velocity is just the momentum derivative of the energy, and the energy current is just velocity times energy times population summed over all bands and momenta. And so all the Hall effect comes from the collision integral. And we consider the inelastic scattering of phonons with other excitations, which yields an extrinsic phonon Hall conductivity, extrinsic but still without any impurities. So the theory we consider is this one. So the total Hamiltonian is the sum of the free phonon Hamiltonian plus the Hamiltonian for some other collective excitations, which we call Q and which can be left unspecified, and their interaction, which we write as the coupling between a phonon operator and some other operator Q. Also, the coupling constant can be included in the definition of Q because Q can be anything. So that's formal, but we can think more concretely, for instance, about spin-phonon coupling. So if we start from a spin Hamiltonian where neighboring spins interact through a magnetic exchange, and the magnetic exchange depends on the distance between the two spins. Now, if there is a phonon coming through, the lattice is distorted, the distance changes, and this generates a coupling between the phonons and this object made out of spins. So in this particular case, the Q operator would be made out of two spin operators and would be proportional to a gradient of the magnetic exchange. Also, one had better include spin-orbit coupling. In that case, this will become important in the following. Okay, but that's one example. Now let's come back to the more general problem of phonons scattering off of other excitations Q, which we leave unspecified. The only assumptions that we make is that the phonons are the only energy carriers, so they are the long-lived excitations that move really in real space and carry energy with them. And the Q excitations, we assume they relax faster to equilibrium than the phonons, and they don't carry energy by themselves, they just act as scatterers for the phonons. Okay, so this is a problem which can be studied using standard scattering theory. So one can compute the collision integral in terms of the elements of the T matrix, which we expanded to second order imperturbation. Hopefully the reason for this will become clear on the next slide. Okay, so this is what we did, and this is what we find. We find that the longitudinal conductivity of the phonons involves mostly these two-point correlation functions of the Q fields, which are scattering the phonons and give the typical inverse lifetime of the phonons. So this is a known result. Now these two-point correlation functions satisfy the fluctuation dissipation relations, and because of that, one can show that they never contribute to this Q scattering of the phonons, which is responsible for the Hall effect. And in fact, the main contribution to the skew scattering of the phonons appears at next order imperturbation and is expressed mainly in terms of these 4-point correlation functions of the Q excitations. So it has 4 insertions of different time points, and it has a lot of structure. One can see there is a commutator and an anti-commutator. And because of this intricate structure, one can show that they are purely non-Gaussian correlations, which cannot be decomposed as a product of 2-point functions as per Wick's theorem. So they are truly 4-point correlation functions. And so this skew scattering rate and this longitudinal scattering, they enter the collision integral, and then we can solve Boltzmann's equation to obtain an expression for the Hall conductivity of the phonons with, as a central object, this skew scattering rate here. Okay, so this is one of our central results, that the thermal Hall conductivity of the phonons from skew scattering mostly involves this very intricate 4-point correlation functions of the phonon scatterers. And I want to emphasize also that this formula only involves equilibrium properties of the system of the Q fields. So for instance, if you think about phonon-magnon scattering, and you want to compute the Hall conductivity of the phonons, you don't need to actually perform the full ab initio calculation of the coupled phonon-magnon system, provided that you know these correlation functions of the magnons alone, either analytically or numerically, then you're good to go. You can plug this correlation into the formula for the Hall conductivity, and you get the result for the Hall conductivity of the phonons. Another point where this formula is quite convenient is that one can see quite directly the effect of symmetries. So we know that if there is time reversal symmetry, there can be no Hall effect. Okay, but why? Time reversal implies some very concrete relations between the skew scattering rates of the phonons, and if we plug this relation into the formula for the Hall effect, we can see concretely that the Hall effect vanishes. And the same kind of reasoning works also for spatial symmetries, for instance, mirror symmetries. Okay, so these are analytical formal statements one can make, but we wanted to apply this to a concrete example, so where we actually compute these 4-point correlation functions for a given model. So formally, what we did is we considered phonon-magnon scattering, and the Q operator we expressed as the sum of all possible combinations of B daggers and Bs, where B dagger is a magnon. So this 4-point correlation becomes an 8-boson correlator, which can be computed analytically. So that's a bit formal, but more concretely, we looked at a square lattice antiferromagnet, collinear antiferromagnet, and now the interaction Hamiltonian is a coupling between the strain tensor, which contains the phonons, and some Q operator, which is all possible combinations of the M and N magnetization fields, which describe antiferromagnet, with all the possible coupling constants in front allowed by the symmetries of the crystal. Now one can get a bit more intuition about these coupling constants, again, by using this intuitive picture. If we think about this, we find that the lambda MM coupling, so this one is roughly proportional to the gradient of the Heisenberg exchange, whereas the other two coupling constants are much smaller and proportional to anisotropic magnetic exchange due to spin-orbit coupling. Okay. Also, we want to study Hall effects, so we need to break time reversal symmetry. And in fact, only this term in Q breaks the effective time reversal, which is time reversal times translation by halving itself. And so this term is necessary if we want to get a phonon Hall effect. In fact, if we do the full detailed calculation, one finds that this coefficient is proportional to some anisotropic magnetoelastic constants due to spin-orbit coupling, and also to the magnetization transverse to the ordering, to the axis of the collinear antiferromagnetic ordering. And since the Hall effect is proportional to this constant, we find that the Hall resistivity is proportional to this spin-orbit coupling constant, this transverse magnetization, and other coefficients. So that's a statement one can make, that in a collinear antiferromagnet, to get a phonon Hall conductivity, one needs to put some spin-orbit coupling. Also, based on our knowledge that this constant is much larger than the others, one can also show that the Hall resistivity scales like a 4th power of temperature. So again, these are analytical statements, but since we have explicit analytical expressions for all the quantities, we can just replace all the parameters of the model by actual numbers and plot the thermal conductivity or resistivity. And so this is what we find. So to plot this, we used numbers inspired by this material, CFTD. And so here I represent the thermal Hall resistivity as a function of temperature here in limb scale. So that's the Hall resistivity in the XZ plane, and that's in the XY plane. And here is a log-log plot where we can recover this T to the 4 behavior that we found analytically. So a few comments. First, I'm plotting the Hall resistivity, not the Hall conductivity, because the Hall resistivity better captures the effect of skew scattering without depending too much on the longitudinal scattering. We find that the rho h in the xz plane is of the same order of magnitude, and in fact a bit larger than the rho h in the xy plane. Okay, so this confirms explicitly that phonons as energy carrier do indeed yield such an isotropic Hall conductivity, which was not obvious. And again, these results we obtained using only inelastic phonon-magnon scattering without any impurities. So all these statements are qualitative, but of course we can make quantitative statements because we have the actual numerical values of the resistivity. And from this we can deduce that the Hall angle we find is large. It's of the order 10 to the minus 3, which is what is called large in the experimental literature. Now to compute this Hall angle, we had to compute also the longitudinal thermal conductivity. Okay, so which we obtained as a nice byproduct of our calculations. So to compute the longitudinal conductivity, we need the phonon typical inverse lifetime, which we wrote as the sum of our phonon-magnon lifetime plus some constant parameter, which we put in by hand. And so this is the longitudinal conductivity for 4 different orders of magnitude of this 1/tau parameter. So we find different temperature regimes, which are given only by the intrinsic parameters of phonon-magnon scattering. So in particular, this T to the minus 1 behavior here is not due to umklapp, that's just phonon-magnon. So this we could explore. Also, we wanted to investigate the effect of this velocity ratio between the magnon and the phonon velocities, which we used as a parameter because it can vary a lot depending on the material one is considering. And for instance, for CFTD, it's 2.5. So this is a log-log plot of the Hall conductivity, and one finds that there is even a qualitative change of behavior depending on the value of this parameter with a threshold effect. And above a certain threshold, the scaling exponent, which typically should be an integer, in fact varies continuously with this velocity ratio, which is quite interesting, and especially as it comes, again, only from phonon-magnon scattering. Okay, and at this stage, I must say that all these numerical results we obtained by plugging in numerical values in the computer. So we did our best based on the values that are in the literature and also by making guesses about the magnitude of the magnetoelastic constants. But of course, if we want to make more accurate predictions, we will need accurate numerical values, especially for these magnetoelastic couplings, which could be obtained by ab initio calculations or maybe experiments of some kind. Okay, so this concludes my first part. So in this part, we focused on the thermal Hall conductivity of phonons by inelastic scattering with magnons. I mean, with other excitations first and then specializing to magnons. And we showed that there can be a large thermal Hall effect from extrinsic origin of the phonons from this right-hand side of the equation. And now what we wanted to investigate is also the role of the left-hand side and of the convective derivative. In particular, in our calculation of scattering, we assumed Boltzmann's equation as a starting point, but it would be better to actually derive the full kinetic equation with all the intricacies of the left-hand side from an earlier point. Okay, so that's what Leon presented. So as a starting point now, we don't assume the kinetic equation, we want to derive it, so we start from the Hamiltonian of our energy carriers. So for instance, if we consider phonons, we start from the Hamiltonian of elasticity. So here U is the displacement field, and pi is the conjugate momentum, which is not just the canonical lattice momentum, but we add this object here, and it's called the phonon viscosity. And it's the simplest term one can add to the theory of elasticity, which breaks time reversal symmetry. And one can guess that this will generate some very phase effects because it modifies the commutation relations of the conjugate momentum. Also, we want to derive kinetic theory for inhomogeneous bosons, so all the parameters of the theory are allowed to depend on position. Okay, so that's for the case of phonons as neutral excitations, but one can do the same also for magnons. So then the starting point is the nonlinear sigma model in terms of the M and N fields. And the equivalent in that case to the viscosity would be this term here, which can arise, for instance, from Jaroszynski-Moiré interactions. So those are, again, all the parameters of the theory can depend on position. So that's two examples. Now, as Leon explained, we wanted to consider the more general case of some real fields, which we call phi, which have some given commutation relations and which have a quadratic Hamiltonian of some kind. And given this at the starting point, we want to derive a kinetic theory for these fields. That is to say, the equation of evolution of the density matrix, which one can build out of these phi fields. And so Leon explained how we can use this star diagonalization to find a shared eigenbasis where both the kinetic equation and the current are diagonal. So the evolution of the population in one band doesn't depend on the populations in the other bands, and the current is the sum of the contributions from the different bands. So we have obtained the kinetic equation, first the exact version of it, and then it can be expanded in powers of h bar as a semi-classical parameter. And at lowest order, this is Liouville's equation. And Leon also explained that if we want to go now to the kinetic coordinates, we find that this Liouville's equation features explicitly the Berry curvatures. So with an S, all the Berry curvatures in phase space of the bosonic excitations. Okay, so that's for the kinetic equation. We have also an expression for the phase space energy current as the sum of two gauge invariant contributions, which feature explicitly the Berry connection, and this object, which looks like the energy magnetization. So this is in the free case, but one can generalize this also to the case where there are interactions. Okay, so we have obtained this kinetic theory for thermal transport by neutral bosonic excitations. So now that we have it, we can apply it to compute the thermal Hall conductivity. So since we have the expression for the local current in phase space, well, first we can integrate it in momentum to get the local current in real space. And now we can again integrate it over a slice of material in a finite system to get the total flux of energy through this surface. And by doing this as a thought experiment, we have obtained this formula for the Hall thermal conductivity, the transport thermal Hall conductivity, which looks very much like the TKNN formula for the electrical transport, but in that case for the thermal conductivity of neutral bosons. And as Leon mentioned, this recovers a result that had already been derived differently using linear response. Okay, so this we can obtain as a thought experiment, but in fact we don't actually need to integrate the local current over a slice of material because we have the expression for the local current. So instead we can look at a finite system. So here we considered a system whose bulk is two-dimensional isotropic elasticity with a phonon viscosity to break time reversal symmetry, and we took smooth boundaries to the system and a gradient of temperature. And since we have the explicit formulas for all the gauge connections and energy magnetization and the currents and so on, well, we can plot the actual local energy current, and this is what it looks like. So the two gauge invariant contributions separately. So we can see that it's roughly counter-propagating energy currents along the two edges of the system. And there is a total flux through any surface one may want to drive, so one can recover the thermal conductivity expression from this, but this goes beyond because we have the actual local current. So I plotted this just to illustrate that one can, but now the formalism also is ready for adding collisions and considering more complicated inhomogeneous systems and so on. Okay, so to summarize, so we have investigated the thermal Hall conductivity of bosons, neutral bosons from both sides of the kinetic equation. So first, focusing on the collision integral, we studied the inelastic scattering of phonons by other collective excitations, and we have exhibited this skew scattering rate expressed in terms of these specific 4-point correlations, which provides a formula for the thermal Hall conductivity of phonons by scattering out of any other excitations. As an application, one can prove that in a collinear antiferromagnet, from skew scattering of phonons by magnons, spin-orbit coupling is required to get a Hall conductivity. And this plot here shows that phonons as energy carriers allow for an isotropic thermal Hall conductivity, which is large, with a Hall angle of the order 10 to the minus 3. So that was for the collision part, and also from the intrinsic dynamics, we have obtained kinetic theory for the thermal Hall conductivity by neutral bosons, and which provides in particular formulas for the local energy currents, here in the case of phonons with viscosity. Okay, thanks.
Thank you very much. A very informative talk. So, questions?
Yeah, I was wondering about the peak in the thermal conductivity, Hall conductivity. Is that a bandwidth effect that it goes back down, or what is the?
Here, you mean?
Yeah, the fact that at high temperature goes back down.
No, so it depends. So at low temperature, so it depends, in fact, on the magnitudes of these constants. In fact, on the value of the temperature with respect to some ratios of these magnetoelastic constants, depending on whether the phonons couple mostly at a given temperature to the M fields or to the N fields. Because the M field is the conjugate momentum to the N field, it gets different powers of momentum and different powers of temperature, so you get different exponents depending on the scattering regime where you are.
So you talk about a low temperature, high, or you're talking about the scale itself?
So I'm talking about the temperature at which there is this transition.
Right. But the fact it goes back down, is that a generic effect of?
That's if you, so if you couple phonons only to these M fields without the N fields, then you will find for the thermal conductivity of the phonons this T to the minus 1. Oh, so we don't put any impurities here. Sorry.
Wait. Use the microphone.
So I was just trying to see the same point that Leo raised. So in a classic kind of textbook treatment like Zeiman or Kittel, if you look, this 1/T that you see is regardless of what mechanism of scattering you involve. N field, M field, doesn't matter. Right? So I thought that maybe that's all you're seeing, that at high temperature, that's just a Bose distribution.
Yes, well, right? Ultimately it all boils down to thermal conductivity is thermal capacity times mean free path.
Precisely.
Yes.
Yeah, so isn't that the answer to the question Leo asked? Why it goes down at high temperature? Well, we also apply thermal capacity times mean free path in this region where it increases like T to the 3. So you're not explicitly using that semi-classical formula. You're saying this just comes out from your formalism. No, right. We are using our formulas and then we plot the result. Okay. And that's all we get.
So thank you. Going back to your phonon thermal Hall formula, I want to break it down a little bit. So you say it depends on the spin-phonon coupling strength and the spin-orbit coupling strength?
Yes, so the spin-phonons...
there was a different formula explicitly showing kappa H.
Okay, yes. This one maybe.
Yeah.
Okay. Yes, so in fact, the spin-phonon coupling, it's, oh, sorry. Okay, the spin-phonon couplings, they are these lambda constants here. Now, these lambda constants, they come basically as gradients of some of the magnetic exchange. I mean, you can have an intuition that they come from the gradient of the magnetic exchange. So now, now we know that, okay, this lambda mn this lambda mn constant here, which is necessary to get a Hall effect, one can show, I don't show the calculation here, that it is okay, necessarily anisotropic in spin space and also in real space, in real coordinates. So if we take back this, if we go back to this picture of derivatives of the magnetic exchange, it comes from derivatives of off-diagonal anisotropic magnetic exchange. So from spin-orbit coupling.
Oh, I see. Where is the dependence in the external magnetic field? Is there any dependence on the?
So it's in this transverse magnetization here. If we don't have, I mean, if we have a pure collinear antiferromagnet without any external magnetic field, then this will be 0. But if you take your collinear antiferromagnet and you apply a transverse magnetic field, okay, because of the susceptibility, you can get a transverse magnetization.
So,
so when you look at this model, then you can calculate from this model also the Berry curvature of the phonons, I guess. So you can use this model also to calculate, so that then the Magnon system will imprint Berry curvatures onto the phonons described by some real part of susceptibility, I guess. Did you calculate that? And did you compare the two mechanisms?
So you mean, we consider scattering of phonons with magnons, and this scattering also generates, you say, some Berry curvature effects.
Yes.
For the, so as I remember, I tried to do this with Keltish formalism, but it didn't generate anything on the left-hand side. But that was mostly because I was using, you know, the form given in the textbooks for the kinetic equation. And if we take the form in the textbooks, we don't have this effect appearing on the left-hand side of the kinetic equation. But as we derived now the kinetic equation, which differs somehow from previous treatments, we get this Berry curvature indeed on the left-hand side.
So I would expect that there's also contribution from precisely this coupling onto the left-hand side of your equation. Yeah, so that would be interesting to compare to the right-hand side effect for the same model.
Yes, in fact, what would be really great would be to just do both at the same time and see what comes out.
So I have two more technical questions, maybe. So in principle, this magnetoelastic expansion can continue, and you will get the term which will contain two phonon operators directly without going to the second Born approximation. Is it going to give you higher power in temperature because of the derivatives, or why is it neglected?
So the terms with two phonons, if you take them to the, okay, I can show here. So in here you say this Q operator would contain now two magnons.
No, two phonons. So if you go previous slide, so you have U square, not U displacement. So the expansion.
Sorry.
The elastic,
here, okay.
Yeah, here, yeah.
Yeah, right. Two phonon operators. Yes, that's right. So if we go only to the first order in now Born's expansion, in fact, we run into the same issue that the correlation functions that we obtain here, they still satisfy the fluctuation dissipation relations. And so as far as I remember, they always also drop out of the skew scattering. So we would have two phonon terms, but you would still need to go to the second Born's approximation.
So the second question is that in the CFTD, in the scope performated reduced. I didn't quite get if there are any experimental results. And the second thing is that you are listing some numbers there, some coupling constants, as far as I had time to get. But
Yes.
I'm wondering how you can get them because it involves knowing the derivatives of the exchange couplings, which are typically not known.
Okay, so thanks for your question. So there are experimental results. So this material was studied by Radu Koldea some time ago. So the oh, I don't know about results about the thermal. Okay, no, that's right. So here the spin-orbit coupling, roughly 5% of the Heisenberg exchange. That's from okay, studying the magnetic structure, but you're right, not the magnetoelastic couplings. So I'm just saying that okay, the magnetoelastic coupling is, say, Jaroszynski-Moiré divided by lattice constant, and this isotropic is Heisenberg divided by lattice constant. So I expect the same ratio of around 5%, but you're right, this is just a guess. One would have to measure the experiments, the magnetoelastic couplings.
So related question. So to get 10 to the minus 3 whole angle, so you don't need any assumption. You know all the parameter. Without any adjustable parameter, you can reproduce 10 to the minus 3 for Q plate.
That's with the parameters we picked. But we did not try many parameters till we find 10 to the minus 3. We just started from reasonable parameters, and this is what came out.
So you have to actually say like, you know, strength of skew scattering. Is it kind of, you know, adjustable parameter, or you more or less know what is strength of skew scattering?
Yes, so we computed the strength of the skew scattering from our formulas, and the assumptions that we made were the values of the magnetoelastic couplings, and we did not choose them to get 10 to the minus 3, just we picked them reasonably with the values of the parameters.
So we have strontium-2 iridium-04, similar to lanthanum Q plate, but spin-orbit coupling is 1 order of magnitude kind of larger. And can I expect, you know, 1 order of magnitude, you know, larger thermal Hall effect for strontium iridate? So it's you know, almost, you know, collinear antiferromagnet, but spin-orbit coupling 1 order of magnitude larger.
Well, perhaps.
So I have two clarifying questions for this skew scattering. In this slide for the T0, maybe I missed it. What does that mean? Is that the Magnon excitation energy?
Sorry, say that again?
The T0.
Yes.
What is?
Oh, that's just one scale of energy that we use to plot our data. So it's like if you take okay, the value of, if you take the value of the phonon velocity and the lattice parameter and KB and H bar, this gives you a unit of temperature. That's it.
I see. So it has nothing to do with the energy scale of the magnetic excitations.
No, that's right. It's from the phonon velocity.
I see. Thank you. The second question is I forgot. I will ask you later. Sorry.
Yeah, thank you for the talk. So my first question is this: when you discuss for the antiferromagnet the thermal Hall effect, where you consider two spins and the phonon connecting them, essentially the magnon-phonon scattering, this is qualitatively different from the kind of old phonon thermal Hall effect, right? This Raman interaction where we just have a single spin and then spin-orbit coupling to the. So the environment, I think in that case, only the environment of a single magnetic moment would be important. The 2003 paper by Strom and others. That's qualitatively different from your mechanism, right?
Well, I don't know if that's qualitatively different because, I mean, I don't know where the Raman coupling comes from.
Right, that's true. Yeah, I think it's just a symmetry argument in that case. It's allowed by symmetry, and then they say, okay, we observe it. And then my second question would be the calculation you made for the antiferromagnetic state, where you couple the magnon to the phonon. If you apply a very large magnetic field and you went to some field-aligned ferromagnetic state, this signal would go away, right? Is that correct? So if in a ferromagnet, can the same signal appear or not?
Well, I haven't done the calculation. I don't see any symmetry argument where it couldn't exist.
In other words, why did you choose the antiferromagnet? Just because of the cuprate or for some other interesting reason?
Or maybe because like insulating magnets, most of them, many of them are antiferromagnets, so that's also interesting in itself.
In fact, I already forgot half of my comment, but there was a comment related to questions a little while ago about parameter choices, et cetera, which, I mean, as Leo said, we had to make, some arbitrary parameter choices somewhat because no one knows all these magnetoelastic constants certainly for this material. And what one says is reasonable may also be somewhat optimistic, let's say. I mean, I would regard probably this 10 to the minus 3 as large, and probably, somewhat close to an upper limit from this mechanism, just because we were not pessimistic in estimating those parameters. I think there was something else I wanted to comment on, but I forgot it. So, okay. Anyway.
So for this plot that you were just showing here, did you assume that the staggered magnetization was constant in temperature, or did you actually use the experimentally measured order parameters, functional temperature, over that temperature region?
Sorry, what was constant in temperature?
The order parameter M0 perpendicular. I'm assuming that's the staggered magnetization, no?
No, that's right. We took the parameters once and for good, and you're right. In principle, all these parameters also should depend on temperature. That's right.
That's uniform.
So, but T0 is what now? How does it compare to T
So in CFTD in particular, so I think the three-dimensional ordering, I think it's about 20 Kelvin, I think. The two-dimensional ordering, I think, remains till the crystal structure changes, so 230 Kelvin or something like that.
Leo, a clarifying question. So in this calculation, you assumed an ordinary antiferromagnet for the magnon part, correct?
Yes.
Imagine, so you probably haven't done the calculation, maybe you have, but what would happen if your magnon subsystem had a Chorn number associated with, let's say, one of the low magnon bands?
Okay.
What would change qualitatively in your formalism? Like if you go back to the previous formula, it seems that the end result only depends on what you called M naught perpendicular, so the transverse magnetization. It doesn't seem naively to depend on any Berry curvature associated with those moments, does it?
No, that's right. Okay, I guess the Berry curvature effect of the magnons would appear if they had really, time to propagate a lot. But here we are assuming that they just scatter the phonons and relax to equilibrium. So, okay, maybe that's why it doesn't show up here.
I see. But would you agree it would be interesting to perhaps compare to a calculation where you take a bilinear coupling, phonons and magnons, as has been done in many papers, yes. Right? And you could imagine just tuning your model parameters in such a way that you get a non-zero Berry curvature for this magnon-phonon bands, whatever you call them, right? And then, you compute this using a classical Kubo formula. And then you say, well, can I recover the same result from your formalism? Do you think that would be of interest?
Okay, so I think here, like if you want to study this, then you can just first diagonalize this like bilinear magnon-phonon couplings. You get other excitations with an avoided crossing, And then you can just call this new excitation your A dagger, and you scatter it with something else. So in that case, okay, it would be, you're right, then it would become the energy, like the Berry curvature of the A dagger, and then that's what comes from the last part of my talk and the left-hand side of Boltzmann's equation then. No, you would first need to define properly your eigenparticles, and then derive the full kinetic equation with the full left-hand side for these eigenparticles, and then you will get the whole effect.
Other questions? If not, let's send Leo and all speakers of the session.